Hello, this is my recording for problem set 2 task 1 for the task description. And I'm going to go ahead and show the task description as I read through it. So this task is about computing the amount of fuel that's left in a car and reporting that in text. And the idea is that we have a car with a fuel tank. The car only has a limited ability to measure the fuel in the fuel tank. It can only measure how high the level of the fuel is. So we have some functions for figuring out how much fuel there is based on the height of the fuel in the tank and the shape of the tank. And then we have some further functions that do some extra processing to report the fuel in a certain way. So if you're in the car and you're driving down the highway and you notice that your low fuel light goes on and your tank is at empty, you probably still have like 20, 30 miles that you can still drive to find gas at that point. And that's because your car is tricking you. It doesn't really report the true amount of fuel left, but it sort of reserves some fuel that when the fuel gauge hits 0, there's still actually some fuel in the tank. And this is good, right? Because if you forget and the engine light or the fuel light comes on, you're not just out of gas right there. Like you have a chance to like, oh, where's the nearest gas station? Let me get some gas. Excuse me. So the idea of this task is to write some functions about that. And the point of the task is really to practice writing and calling functions. How do we do these things? So the goal is not necessarily to solve these intricate math problems or anything, but just to get some practice with writing functions and calling them, and having multiple functions that call each other that we are going to write. So that's the idea of the task. To make the fuel part interesting, we say that there's a conical fuel tank. It's not very realistic, but that's what we say. So that the fuel tank in the car is this cone shape with the pointy end pointing down, right? So the fuel can drain out from the bottom very easily. And we have a diagram here that the fuel tank has a 60-degree radius for this, or 60-degree angle for this cone from the horizontal. So the sides of the cone are pretty steep. And the diagram is showing that if the radius of this cone is 1, then the height will be the square root of 3, and the edge length will be 2 units. And the ratios between these values, because of similar triangles, are going to apply to any cone that has the 60-degree angle. So the fuel tank will have a certain height to it, and then the amount of fuel in the tank will have a different height value. And we can use those two height values along with the formula for the volume of a cone to compute how much fuel is in the tank, and also what proportion of the total fuel is left, right? Is it half a tank? Is it a quarter tank? Something like that. So for subtask A, we're doing some functions regarding this measurement of fuel itself. And there are 3 functions you need to write. There's a function called cone volume, and it just does the mathematical formula for a cone, right? And that formula is V equals pi r squared h divided by 3, where V is the volume, r is the radius, h is the height. And there's a variable math.pi that you can use for that constant pi. So the function is supposed to take 2 arguments, the radius and the height, and return a numerical value, which is the volume of a cone that has that radius and that height. So it's a function that is a fruitful function. The second function you're supposed to write is called fuel volume. And the idea is that we know that the tank is at this 60-degree angle. So given the height of the tank, or the height of fuel within the tank, we should be able to calculate the amount of fuel. And of course, this function is going to use that same formula for the volume of the cone. Instead of repeating that code, we're going to call the cone volume function that we just defined. Fuel volume, though, only has one parameter, the height. And so it's going to need to figure out, for that height, given the 60-degree angle, what is the radius that corresponds to that? And again, you can use that proportion. If the radius is 1, the height is the square root of 3, right? So if the radius is 2, the height would be 2 times the square root of 3. You can use that proportion to figure out, for a given height, what is the radius. And then you'll have this height and the radius values. You can plug those into the cone volume function, and get your result for fuel volume. So fuel volume also takes a one parameter this time, just a number for the height, and returns one number for the volume of fuel in a cone of that height. Third function for this subtask is fuel fraction. So we don't just want to know how much fuel there is, we'd like to know how much of a full tank we have. So convert that number from an absolute volume of fuel into a fraction of a full tank. And this function takes two parameters. It takes one parameter for how high is the fuel within the tank, right? That's what this car can measure. It has a little floater that sort of measures how high the fuel is. And then another parameter for how high is the tank itself, right? So maybe we have a 10 centimeter tall tank and there's 7 centimeters of fuel in that tank. We don't really care about the units as long as they're the same. So two numbers, input, two parameters for fuel fraction. And the output of fuel fraction should be a number between 0 and 1, so a floating point number, representing what percentage or what fraction of the tank is full. And you could solve some complicated mathematical formula involving the formula for the volume of a cone and all this thing to figure out how to do that. But we have a fuel volume function that we just finished writing. So in fuel fraction, you must call the fuel volume function twice. Once to compute the volume of the fuel based on its height, and another time to compute the volume of the whole tank based on its height. And then you can just divide those two volumes to figure out how much of a full tank do you have in terms of the volume of fuel. So again, two inputs, the height of fuel and the height of the tank, one output, a fraction between 0 and 1. How full is that tank? Okay, there's some notes here that I'm going to go over quickly. One, each function must include a documentation string. This is something we require basically throughout the whole class. So get used to those. That's a string on the first line of the function describing what the function does. And it's useful to describe in your own words what the function does and to even fill out that string before you start writing the function so that you just have clear in your mind what you're doing. There's a rubric that I'll go over at the end with detailed requirements for each of these functions. Another note, there is, each of these functions is just a few lines of code, right? They're not that complicated. But we do have tests for them that are included at the bottom of fuel.py. And you can even add your own tests there if you want. There's a function that's called test. And if you want to add tests, that's where you should add them. That's where our existing tests are placed as well. Also, the functions here don't really make sense if you give them arguments that don't make sense. So if somebody gives you 0 as the height of the fuel in the tank, 0 as the height of the whole tank, right? So it's like a tank, but it's actually not a tank because it's not, there's no height. It's fine if your function crashes. That's not a sensible argument to give. Or like a negative height of the tank, for example, or a negative fuel height, right? It's fine if your function does something weird in those cases. We're not going to test them with inputs like that. All right, another note. So this is just a reminder, which I already went over, that the cones of different sizes will have an identical ratio between their radius and their height, right? So that's the sort of mathematical key you need to figure out the formula you're going to use. There's some example outputs. I'm not going to read through these because they are very detailed, but you can look at them on the problem set webpage yourself. These are also tests that are given in the file. Okay, another note here, your outputs do not have to match the example outputs precisely down to the last digit. There's some imprecision in the way that floating point numbers are handled that we've talked about. As long as you match to within 3 significant figures, so within the first sort of like 3 non-zero digits, your answer will be counted as correct. Okay, so that's subtask A, which is doing these calculations of how much fuel do we even have in the tank based on what the car can measure, which is the height of the fuel in the tank, and of course it knows the height of the tank itself. Subtask B is about reserving fuel and then computing the range, so how far can we travel. And so there's 2 functions to define. One's called conservative fraction and one's called range remaining. Conservative fraction is a function that's motivated by this idea that I talked about, that like running out of fuel is bad, right? So we don't want to do that. So we want to sort of trick the driver into thinking they have less fuel left than they really do. So when they run out of fuel, they think, right, they still have enough to get to a gas station. And so the conservative fraction function works like this. You give it a fraction of a tank. So like, let's say 50% of a tank, 0.5 as the fraction, right? And you also give it a number for how much of the tank you want to reserve, how much you want to keep in reserve. So maybe you say, well, I'm really conservative. I want to keep half of the tank in reserve, and my reserve value is 0.5. And right now, I have 75% of a full tank. So my fraction is 0.75. In that case, what the conservative fraction function does is it says, well, let's pretend that this reserve doesn't exist. And I will give you back a new fraction, which is what fraction of the non-reserve fuel amount is left over. So in this example, if we have 75% of a full tank in our tank, and the reserve amount is 50% of a tank, well, we only have the other 50%, right? The other half of the tank is the sort of like fuel we're going to pretend is all that's there. And out of that 50%, the top half of the tank, since we're at 75% of a whole tank, we are actually at 25% empty, right? And so we have half of that unreserved fraction remaining. And so the result of conservative fraction in this case would be 0.5. Another way of thinking about that is like 75% is halfway between 100% full tank and 50% reserve value. And so we want to know how far between the reserve threshold and the full tank are you, instead of how far are you between 0 and a full tank. Now, one twist in this function is that if the fuel level remaining is less than the reserve value, so let's say that there's only 10% of your fuel remaining and your reserve value is supposed to be 20%, we want this function to just return 0. Just pretend that there's no fuel left. We don't want it to go negative or anything like that. And to do that, you may need to use the max function. So that's the conservative fraction function. You're going to have to sort of, do some little formulas to make sure that we measure a fraction between the given reserve fraction and 100% instead of between 0 and 100%. And again, it's a function that takes two numbers as inputs and gives you a number back as the output. Okay, the tips here, as I already sort of covered, to avoid returning a negative number, which you have to do, you can use the max function with 0 as one of the arguments. And then also, conservative fraction won't work if the reserve fraction is 1.0. If you try to say, oh, I want to reserve the whole tank, right? Because then there's no room between the top of the reserve and the top of the tank to measure where you are in there. So that's another invalid input. We're not going to test with that input. You don't have to worry about what happens with that input. There's one more function that we'll need for our final status report function for this task, and that is called range remaining. And the idea is that if we know how far we've traveled and how much fuel we've used, we can estimate how far you can drive with the rest of the fuel you have remaining. So this function is going to take two parameters. Again, they're both going to be numbers. The first number is a distance. So it is basically how far have we driven so far. And you can treat this as like a number in kilometers or miles. Doesn't really matter what the units are. I think we use kilometers for the output. So given a distance value, and then the second parameter of range remaining is going to be a fuel fraction. So how much of a tank do we have left, right? And we've been writing a couple functions that deal with these fuel fractions. The range remaining function's job is to report how far can we go with the rest of the tank. So simple example, if we've gone 100 kilometers and we've used half our fuel, so the arguments are 100 and 0.5, well then our estimate is we can go another 100 kilometers with the other half of the fuel, right? And so in that case, our estimate would be 100 kilometers. If we had gone 100 kilometers and only used a tenth of our fuel, right, then we'd estimate we can go another 900 kilometers, right? 9/10 of the tank remains. We went 100 kilometers on 1/10. So if we can go 100 kilometers per tenth, we should be able to go 900 kilometers on the rest of the fuel. And there's some other examples here in the website if you want. So that's how range remaining should work. We have another note here that it'll break if you give it 1.0 as the fuel fraction, right? Because if no fuel has been used, presumably we haven't gone anywhere, but it doesn't make sense to calculate how far we can go. And again, it's fine if your function does whatever in that case. You don't have to worry about that case. So once you have defined the conservative fraction and range remaining functions, you're ready to put everything that we've done together into the final subtask. So that was subtask B. Subtask C is on reporting the fuel status. And for this part of the task, we're going to print some messages. So the functions we've been writing so far have numbers as their inputs and outputs, right? And they're calling each other in various ways. The functions that we're going to write now are going to, it's just one function, report fuel status. It's going to take some numbers as inputs, and then it's going to print stuff, but it's not going to be a fruitful function. So this function is going to have 4 parameters. The first parameter is distance traveled. How far have we gone since the tank was filled up? Now, that's the same kind of thing you might need for that range function, right? So we might be using that function with that parameter. Function parameter 2 for report fuel status is fuel height. What's the height of the fuel in the tank? And again, you'll recognize this. Hey, I have an idea of where I could use this parameter value, right? We've written a function that deals with fuel height. Parameter 3 is tank height, right? Same deal. Probably you could use those two things together to compute the fraction of the fuel, right? We have a function for that. And parameter 4 is the reserve fraction. So what fraction of the tank are we treating as a reserve? And we're going to sort of lie to the driver and say, oh, we only have 1% left, right? When we really have like 21% left, if the reserve fraction were 20% or 0.2. Okay, and what does this function have to do? Well, it has to print 3 different messages. One about the current fuel level, one about the range remaining before the reserve comes into play, and a final message about how much range the reserve fuel will give us, just in case we get into that situation, or maybe we're already in that situation where we've burned through all the fuel, it's reporting empty, and we want to know, hey, how far can I go to find gas? So there's examples of the outputs in the problem set, and you're going to have to match them. So I will describe them roughly, but this description is not enough for you to match them perfectly. The first example is, and I'm just going to do the first one. If we do report fuel status with the arguments 100 for the distance traveled, 100 kilometers, 14 for the height of fuel in the tank, so 14 centimeters of fuel in the tank, 16 for the height of the whole tank, so 14 out of 16, that's a lot of fuel, right? And 0.1 for the reserve fraction, so we're going to hold 10% of our tank in reserve. The report should read as follows. Your tank is at 63% capacity. That's line 1. Line 2, at the current rate, your range is 172.66 kilometers. Then line 3, you should be able to travel about 30.3 kilometers on the emergency reserves. So that's our 3 lines of output is the percentage in your tank, reported as a percentage, not as a fraction. The range of your vehicle based on that fake percentage. So both the first 2 lines are based on that conservative fraction, not the real fraction of fuel. And then the last line, you should be able to travel about 33.3 kilometers on the emergency reserves, is based on the amount of emergency reserves rather than the amount of fuel. Although, one wrinkle here is that if your fuel is below the reserve point, and so I'll give you an example of that. If you call report fuel status with 588 as the distance traveled, 1.0 as the centimeters of fuel left in the tank, 12.6 as your total tank height, right? So we've only got 1 centimeter of fuel remaining out of 12, and 0.05, so 1/20th as the reserve amount. It should report the following. Line 1, your tank is at 0% capacity, right? It's not really at 0, there's still a centimeter of fuel, but we're reporting that conservative fraction, which has made it down to 0 because we're eating into the reserves. And then line 2, at the current rate, your range is 0.0 kilometers. Again, reporting based on that 0% capacity, which is the fake value. And then the third line, you should be able to travel about 0.29 kilometers on the emergency reserves. Now, if the emergency reserves were full in this case, we're 1/20th of that 12.6 centimeter tank, it should be 29.55 kilometers that we can travel. But we've drained almost all of the emergency reserves. We're down to our last drops of fuel here. And so that last line of output should report the actual distance you can travel on the remaining emergency reserves if they've already started to be used up. If they haven't been used up yet, then you should report the distance estimate for the full amount of reserves. Okay, some notes on this last and hardest piece of the task. If the fuel height argument is the same as the tank height argument, your tank is full, or if the reserve level is 1.0, this function won't work for the same reasons we outlined above. And that is fine, right? You don't have to worry about that. We're not going to test that. That doesn't really make sense as a situation, so we're just going to pretend that it will never happen. Okay, note number 2, for full credit, your program must reproduce the exact output as seen in the problem set. So you'll have to pay attention to that. What are the words that we use? Where are the spaces? Where's the punctuation? All of that. But that's just an extra goal, so you can get all the core goals without making it be exact. Okay, note number 3. The fuel remaining is calculated as a fraction between 0 and 1, but it is displayed as a percentage between 0 and 100, rounded to the nearest percent. So there's some rounding here, and it's rounded, not truncated. Next note. All ranges reported are rounded to 2 decimal places. Some of the things I talked about only had 1 decimal place. That's because they had an even number after that. But the rounding that we'll do is to 2 decimal places. And there's an extra part to this note. Be careful not to round values before doing calculations with them. The calculation should be performed on the unrounded, precise as possible values. It's only when we are printing the output that we should round them to make it easier for the car driver to understand. Next note, the amount of fuel remaining reported is the conservative fraction of fuel remaining, not the actual fraction. And I already talked about that a little bit. Next note, when the amount of fuel drops below the emergency reserve amount, the reported amount and range are both 0, but the range available on emergency reserves continues to decrease and reflects the actual range estimate based on how much fuel is really left. That's what I already talked about. Okay, next note. Computing the reserve range when the fuel is above the reserve level is complicated. You will need to estimate how many miles the car would have traveled by the time the reserves begin to be used in order to use the range remaining function appropriately. And then it says, luckily, that's something that you will already be estimating for another purpose. So there's a little bit of a hint there. That part is complicated. Feel free to ask about it if you get stuck with it. And then the last note here is saying to compute the amount of reserves actually remaining, but not let that value go above the specified reserve fraction, you can use the min function, which you will need to use in this part. You do not need to use conditionals or booleans in this problem set, which is something that we'll cover later this week, or at least sometime in a future lecture. So you don't need to use those for this problem set. Okay. There's one last part of the problem set description about testing. It says every function you write needs to be tested, and for this task we have provided many of the tests that are shown above in the starter file to be run automatically when the file is run. These are in a function called test, which is where you should put all of your testing code. Testing code outside of that function may interfere with our grading process, but testing code in the function will not unless it causes a syntax error or indentation error. So when you're writing your own tests, if you're going to do that, which you probably should if you have time, put those in that test function. And it also says if you're working on the first few functions, you can comment out some of the other tests, just so that your program isn't crashing all the time. Or that if it is crashing, it's crashing because you made a mistake in the code you're already writing, not because you haven't written one of those functions yet. As usual, when you're done, submit it via the Ocean server. The submission instructions are the same as normal. Last part of this recording for task 1, I'm going to just walk through the rubric, which contains the actual details you'll be graded on. So, core goals for this rubric are 1, all functions must be documented. You must have a documentation string as the very first thing in each function. And our style guide talks about those doc strings. We've also talked about them in lectures. Core goal number 2, the results of cone volume should be correct, and we'll test this in 3 different contexts. We don't tell you what those contexts are. Some of those may be the same as the example test we've given you. Some of those may be different. Typically, the core goal tests are the same as tests we've already given you, or very similar, and the extra goal tests may test a few other cases that you'll only think about if you actually think about what the possibilities are for the function. All right, core goal number 3, very similar. The results of fuel volume function must be correct. And there'll be 3 different tests for that. The results of the fuel fraction must also be correct. That's the next core goal. And there are going to be 3 different tests for that. The results of the conservative fraction function, there's also 3 tests for that. And then 3 tests each for the range remaining and report fuel status functions. For report fuel status, we're testing what it prints, not what it returns. For the other ones, we're testing what it returns. Okay, more core goals here are you better define the cone volume function, right? So this is not does it work, but did you define it? And then our only requirement for that function is that you must use a return statement. That's really just a hint. You're going to need to return in almost all of these except for your report fuel status function for them to work correctly in any case. All right, core goal number 10, you have to define the fuel volume function. And the sub-goal here is that function must call the cone volume function, which is sort of something I discussed in how you should go about that. Core goal number 12, you must define the fuel fraction function, and the sub-goal here is that that function, fuel fraction, has to call fuel volume. So we're setting up these requirements that the different functions usually each call the previous function, or one of the previous functions, to do some of their work, instead of like copy-pasting that code or other ways that you could do it. All right, next core goal, you have to define the conservative fraction function. And our goal for that one is within that function, you must call the max built-in function, at least once. All right, next core goal, you have to define range remaining. We have no requirements for what you have to do inside of range remaining, although, as I already said, the results have to be correct. All right. Last and most complicated core goal, you have to define report fuel status. This has a couple of different things you have to check off within it. So, report fuel status must call fuel fraction. It must call conservative fraction. It must call range remaining, right? So we're sort of using these different functions we've defined to put together a more complicated function. And then it has to call print and it has to call round. And as long as you fulfill all those criteria, those are your core goals. For the extra goals, we have 3 more tests each of cone volume, and fuel fraction, probably with more interesting inputs. We have 7 different tests for conservative fraction. We have 4 different tests for range remaining and 6 tests for report fuel status. So these are the more advanced and trickier tests to get right. Notice that none of these tests will test any of those weird inputs that we said in the problem set description we're not going to test. All right. Other core goals are about the definitions of functions and how exactly you should define them. So an extra goal is that for fuel fraction, you should call fuel volume in exactly 2 places rather than just at least once. Another goal is that for conservative fraction, you should call the max function not just at least once, but in exactly 1 place. Another extra goal is, this is actually the final extra goal, and the final goal overall is for report fuel status, but it's a little bit complicated. So it has several different sub-goals you have to satisfy, and they're similar but with limits. So you have to call fuel fraction in exactly 1 place. You have to call conservative fraction in exactly 1 place. You have to call range remaining in either 2 or 3 places. You have some flexibility there. You have to call print in exactly 3 places, round in exactly 3 places, min in exactly 1 place, and then you must not use a return statement, which wouldn't be useful anyway because all this function has to do is print. It shouldn't be a fruitful function. All right, those are the rubric goals for problem set 2, task 1. I'm going to stop this recording here and make a new one for problem set 2, task